Okay, well, GDevCon Europe. It's great to be here. Thank you to the organizers for accepting my abstract for this presentation. For those of you that don't know me, my name is Peter Scarf. And today I'm going to be talking about one of my favorite topics, which is object-oriented programming. And the inspiration for this presentation came from kind of a pain point that I had when I first started using object-oriented programming. I was taught what an object was, how to use it, but not exactly where to use it. Objects are very powerful things, and you can pretty much turn almost everything into an object, but the question is, should you or should you not? Hence the name, hence the title of my presentation, To Object or Not to Object. That is the question. Yes, it is a play on from William Shakespeare's famous line, to be or not to be. That is the question in the play Hamlet, where Hamlet says this, he has to make a choice between two fundamentally different paths. To be, to endure the suffering of life, or not to be, to die and face the unknown of death. And we as LabVIEW developers also kind of come to a fork in the road when we are programming. Should we use an object to model and represent something in our code, or should we leave it as a simpler construct, such as a scalar, typedef, library, etc.? And the decision we make here is an important one because it often leads to serious repercussions down the line in our code. So to help us decide and understand when we should use objects and when not to use objects, I thought I'd go back in time, back to the 1960s, to a time where there was no objects available because the programming language at the time were just procedural, such as Fortran and COBOL. At this time, the discipline of computer science was relatively new, and the programmers were having a big problem. The applications at the time were large, monolithic applications consisting of hundreds of functions all poking at the same global data. And as applications scaled, they became increasingly complex to manage. So the computer scientists needed a way to decompose large applications down into smaller, more manageable parts. So along come two very smart Norwegian computer scientists named Kirsten Nygaard and Ole Johan Dahl. And I apologize to the Norwegians in the audience. I'm sure I just completely messed that up. And they introduced the idea of objects being a blueprint that bundled data with the code, the behavior that acted on that data. And they call them objects. They created the first official object-oriented language called Simula 67. And Simula 67 was kind of a very important point because it kind of forever changed the way that programs would be developed from that point forward. Moving on to the 1970s now, let's meet LNK, which Nico also had a quote from Alan in his presentation. Alan Kay was also a computer scientist. He also created another object-oriented programming language called Smalltalk. Alan didn't like the way objects were being used at that point in time, with a large focus on complex inheritance hierarchies. For Alan, OOP wasn't just about objects, it was also about messaging. And I quote, "I thought of objects being like biological cells and/or individual computers on a network only able to communicate with messages." They call him the father of object-oriented programming. Supposedly he was the one that coined the term object-oriented programming. Later on in his career, he actually said that he wished he actually had called it message-oriented programming because people had placed too much of an emphasis on objects and not enough on the communication between objects. So for Alan, object-oriented programming came down to three main things. We have two objects. The first is that objects protect their own data and their own state. External entities cannot go around and poke into the data and change it of an object. Objects communicate via sending messages to one another. Yes, you can call an object's method directly from another object, but his original intent was that objects communicate asynchronously by sending messages to one another. Think of a queued message handler. Thirdly, that object behavior is deferred until runtime. He called this late binding. We know it as polymorphism or dynamic dispatch. So, 4 big ideas worth keeping of what object-oriented programming was meant to be. Number 1, composition, decomposing large problems into smaller, more manageable parts called objects. Number 2, objects protect their own state and their own data. 3, objects communicate with each other by sending messages to one another. And 4, polymorphism. And that is the same message can produce different behavior depending on the object that receives the message. This all sounds great. Object-oriented programming often gets a bad rap. I think it's very important to understand where to use it by understanding the purpose that it was created for. You can also use objects in a way that makes your code, especially in LabVIEW, a bit more bloated. LabVIEW is a specific use case. It's often easier to use objects in kind of multiple or more often in other programming languages. But let's stick to LabVIEW for now. First of all, we have the anemic class. The point of a class is to bundle data with the behavior that acts on that data. An anemic class just contains data. And get and set functions is not behavior. Read and write VIs is just a way to access the data. The problem with this kind of class is that the behavior that acts on this data is external to the class, not within the class itself. Do we really need to, therefore, put just data with get and set functions into a class? I would suggest it's just better to leave it as a scalar or a type def. Yes, I've seen a Boolean put into a class with a read and write access of VI that's only ever used once, when a bool could just be used instead. So, yeah, keep it simple if you can. Number 2, Nico also touched on this, is the inheritance jungle. Large, complicated, huge inheritance hierarchies. We've all seen this. This happens when you add behavior to a base class, and then you create another class which inherits from the base class, you add more behavior, and so on and so forth. The problem with this is that any changes in the base class will affect all the other classes that inherit from it. This makes your inheritance hierarchy decoded very fragile, complex to understand, and hard to follow. What's a better solution is to use composition when we can. So we're going to add functionality, add additional behavior to a class by getting it to use the behavior of other classes. For example, a car has an engine, a wheel, and lights, and doesn't inherit from these. Inheritance is great, just use it carefully and try and keep your inheritance hierarchies as shallow as possible, and use composition when you can. And simply always try and use the simplest tool that works. Not everything needs to be a class. Just because you can bash a screw into a piece of wood with a hammer, if there's a better tool that can do the job more elegantly, simply, then use that instead. Not everything needs to be a class. So here are 4 rules of thumb that I use when I'm trying to decide whether to turn something into whether to use an object or not. So if we just have a single value, a scalar used to represent temperature, mass, velocity, displacement, etc., then just use a number or a string or a path or something like that. Keep it simple. The point of a type def is to define the shape of data. They provide structure to your data. And use them if you need to define the shape of data in multiple places throughout your code. For example, configuration data will be made up of a bunch of scalars usually. The purpose of a library is for organization. Libraries also provide namespacing and scope. Use them when you want to combine a bunch of VIs, type defs, and classes that all kind of do the same kind of thing, such as file I/O utilities, read file, write file, delete file, move file, etc. And fourthly, when you're going to create something that's going to do something, that's going to have behavior, then use a class. The point of a class is to bundle data with the methods that act on it. So if you have some data and you want to do something with that data, then you're going to have an API using verbs. Start motor, stop motor, reset motor. These are all verbs. So if you're using verbs to explain your API, then you should use a class. So there are my 4 rules of thumb. Now, what's the point of all this? The point of all this is that when you use OOP correctly for the right things, it will reduce the complexity of your architecture. That's why classes were created to actually solve a certain problem, to make applications less complicated. So before object-oriented programming was around, the applications were rigid, repetitive, and difficult to scale. But if you're using a lot of anemic classes and classes everywhere, when you can instead use a simpler construct, then your code will be bloated, it will be hard to read, and it will be very frustrating to debug. But when you find the sweet spot and you're using classes only where they need to be used, then your code will be cleaner, you will develop faster, it'll be easier to debug, and most importantly, we will have happy developers. So that's the first part of the presentation. The second part of the presentation is about how the workers framework uses classes, and I'll explain where it uses classes and where it does not use classes and why. So for those of you that don't know what the workers framework is, Workers for LabVIEW. Workers for LabVIEW is an asynchronous modular framework for LabVIEW, and it's been specifically designed to help you create large, scalable, asynchronous applications in LabVIEW. Workers for LabVIEW is built on 4 main pillars. The framework architecture is built on 4 main pillars, and I'm going to explain each of these now. The first pillar is the development style, which is the NI QMH development style. Why did I choose this? Because it's familiar to virtually everyone in the NI community. It's accessible. It's proven itself over many decades. The QMH actor framework, they both use queued message handlers. Most homespun frameworks that I've seen are also some kind of variant of the NI queued message handler development style. A worker in the workers framework is an asynchronous process in the workers framework is called a worker. Every worker contains a main VI. And this is the code on a worker's main VI. Should look like a standard queued message handler, like in the continuous measurement and logging sample project that ships with LabVIEW. Event handling loops are optional. Message handling loops are mandatory. Events come in, is this going to work, into a worker's queued message handler here at this VI. This VI is called DQMessage. Message payloads are simply type defs. There's no behavior that is sent with the message, so it's not a class, it's just a type def. It's just data. The behavior, the code that acts then on the message data, is provided by the worker itself. It's not in the message. It's provided by the cases in the message handling loop. So message payloads are type defs, and again, the data is acted upon by the logic within the worker's message handling loop. And this is the development style. So every worker in an application is going to have one of these. We're going to send messages around, and we're going to manipulate the data in the messages in our message handling loop. Number 2, the second pillar. Each asynchronous process is an object-oriented, well, it's a class. This is the only place that we actually use classes in the framework. Messages are type defs. The modules, the asynchronous processes, they are classes. And this greatly simplifies the architecture, and I'll explain why. And I know a lot of people, people come to me and they say, I don't have any object-oriented programming experience. Can I use the framework? And I say, yes, absolutely. Most of the time, in the LabVIEW Core 3 course, you'll learn about the queued message handler template. The template is a queued message handler in a main VI, in a library. We have some support VIs. We have some type defs. We can create a public API for it. So I say, just think of a LabVIEW class as a LabVIEW library with superpowers. Okay? And if you notice now, we actually have a class on the left side, not a library anymore. So the structure of the way we interact with our code is exactly the same as it would be if it was in a library, but we can also use a class for organization, for namespacing, and for scope. The great things about using a class instead of a library is, number 1, a class is a LabVIEW data type. We can create multiple instances of the same class. If we drop 2 class object constants onto a block diagram, press run, we'll create 2 instances, 2 objects of that class. Number 2, we have native encapsulation. We have a type def, which is tied to the class. Data in this type def, in this cluster, cannot be accessed by any VIs external to the class. We have the same structure. We have our messaging public API VIs, and the behavior, the logic that acts on our encapsulated data is contained in our main VI. What are the LabVIEW class superpowers? Well, these are the standard the standard class features. Number 1, we have inheritance. Inheritance is great. It means that our code base is significantly smaller. Every time you create a new worker, every worker has 1 VI, its main VI. This is the only VI which is unique to every new worker. All the other VIs that a worker uses, DQ message, error handler, shut down, and clean up, is contained in a common base class. So when you have many workers in your application, every worker will be created with 1 VI. Inheritance is great to keep common boilerplate code out of each of our workers. Number 2, we have abstraction through inheritance. This allows us to separate a worker's public API from its implementation. This is great for creating hardware abstraction layers. We have polymorphism, again, allows us to decide the behavior at runtime, not at compile time. This enables plug-in architectures. And again, we have encapsulation, which protects an object's state and data. The third pillar, structured modular hierarchies. So workers are not designed to exist in isolation. They are designed to plug together to form large, scalable trees. This produces clean, scalable architectures, and messages are sent over the tree like in the actor framework, so we also have very clear messaging pathways. Why? So this is a little bit inflexible for some developers. In the beginning, when I started developing frameworks, I didn't have a way to plug my workers together. And I was like, okay, I'm going to do it right this time, but I'm a very lazy programmer, so I always end up creating this. Because I have 1 worker, 2 workers, 3 workers, okay, I'm just going to send messages to each other, add on another one, oh, he's going to also communicate with all of them, add on another one, more, it scales, it grows, and you produce a spaghetti architecture. That's what I call it. So with workers, this is the way it works. So say we have a list of, 12 workers in our LabVIEW project. I will select one as the head worker for our application, and then I'll use the create add worker tool to create new workers and plug them into the workers in our application to form a tree, which is the basis of that is our application, basically. And again, messages are sent not directly from one worker to any other worker, but over the tree. And this diagram here is actually created for you by one of the scripted tools in the framework. What this tool does is it iterates through all the workers in your LabVIEW project and will produce the call chain diagram for your workers, which is what you see here. For those of you that actually have used workers before, you might notice something different in the project here. The icons for each worker is now this little blue person. It's not a LabVIEW class. There is a third-party toolkit, which is actually coming out for the framework, which has been developed by a smart, very smart developer in the United States. So be on the lookout for that. That's going to come out soon for the framework. Pillar number 4 is plugin architecture. We can plug workers into our application, into our tree at runtime. This allows us to swap functionality and behavior of our applications without rewiring anything. So, an example. Let's say we have a workers application defined by this worker call chain hierarchy here. You will notice that not all of these is actually a worker. One of them, this guy here, is actually a worker base class. You can see that from the key in the top right corner. Every worker is plugged into its caller via the worker's public API. You can also create, though, a public API in a worker base class, and this is an API abstraction or a hardware abstraction layer. And this is really cool because what it means is that at runtime, we can choose which worker we want to run on our API abstraction. So we can plug in at runtime a simulation motor, code that's going to simulate a motor, or then we can unload it and plug in on the same hardware abstraction layer a worker which is actually going to talk to a real hardware device. So this is polymorphism in action, and this is all scripted for you. You can create hardware abstraction layers using the tools. And because it's a native OOP framework, because we're using classes for our asynchronous processes, it's very easy to do this. You don't need wrappers or anything like that. It's built directly into the framework. Thank you. Any questions?
Cheers, Peter. At the front.
Yes, Tom. Hello.
Hi, Peter.
Yeah.
Thanks for your presentation, and I agree with everything you said. I think I'd also like to append the notion that when using type defs in LabVIEW, in the IDE, it's very difficult to keep track of all of the locations where those type defs are being used.
Yes.
And so very often I would use like anemic classes to get and set type def data because it is easier to track down methods than it is individual bundle by name functions. And also when messaging, if you're messaging using a type def, then suddenly 2 of your modules are dependent on this public type def.
Yes.
And it can get lost. So very often I will be very strict in keeping type defs private to my class or module. But yes, that's...
Okay, yeah, LabVIEW is like, I mean, I started developing in C and C++, and then you move to LabVIEW, and then you realize that there's not everything translates from one language. It's like a joke. When you try and translate a joke in different languages, it often doesn't translate well. So there's better ways. The finesse is required. Yeah. Thanks, Tom.
Hello, Daniel.
Hello.
Yeah, thanks for the talk. That was interesting. I couldn't quite work it out. With the workers being classes, can you build them up with inheritance the same way that you can in the actor framework? Or is it that because their behaviors are in the main? It's not an option.
You build them up with inheritance, like in the actor framework.
Yeah, so like in the actor framework, you can like establish certain behavior in the actor core, and then have another actor inherit that behavior, and then build on that.
Oh yes, absolutely, absolutely.
Okay.
Yeah, you can do that. Yeah. So if you want to have a bunch of behavior, a bunch of functions, you can create them in a worker base class, and then all the like open main VI. You can create it in a worker base class, and every worker that inherits from that, you can also call that function on it.
Fantastic.
Yeah.
Okay, thanks, Peter. Cheers.
Thank you.